Hello, everyone. My name is Shikang Liu from CSIRO, Australia. Because the others cannot attend this conference, and I will present their paper on their behalf, and the title is DNN-GP, Diagnosing and Mitigating Models Fault Using Latent Concept. Let's start with some background of machine learning. In machine learning, we first have some training data. Then, together with a learning algorithm, we can train a predefined machine learning model. After training, the model can be deployed in many applications, such as advanced chatbots, advanced image generator, and even video generator. However, although machine learning models achieve great success, their robustness remains a problem. For robustness in machine learning models, the most well-known is adversary attacks. A well-trained model can recognize the pattern well. However, when the pattern is added with some imperceptible noise, the model can't recognize it anymore. For example, recognizing it as a cat, in addition to adversary perturbation, the model is also sensitive to data corruption. Specifically, when a normal sample is corrupted by noise or blur, the model may also not recognize it. So here is a research question: how do we interpret models' faults? That is, how to understand the model's mistakes on the adversarial examples. We do have existing solutions using grid cam technicals. Specifically, we can use this technique to visualize which part of an image are most important for the model's decision making. When a sample becomes an adversary example, by adding imperceptible noise, we can observe that the model is making decisions based on background information rather than the objective itself. However, although we can visualize the important features, we do not understand the high-level root cause of the misclassification. That is, we don't understand what the noise means in a structured manner. So in this paper, we propose our solution in DNN-GP, which uses latent concepts to diagnose models' fault on adversarial examples. In summary, DNN-GP diagnoses adversarial examples by mapping them to a latent conceptual space and compare them with normal samples. Specifically, DNN-GP has an encoder and a decoder, together with a pre-trained code book. We first map the normal sample into a vector representation matrix using a pre-trained encoder. Each element in the vector representation matrix is a d-dimensional vector. We have a pre-trained code book with each concept captures the structure attribute of the sample. For example, a concept represents the black background of the number 7. Because each concept is a d-dimensional vector, we can use a vector equalization technique to map the vector representation to a concept matrix. For given adversary example, we can follow the same procedure to obtain its concept matrix. Because adversarial samples are essentially different from the normal samples, the concept matrix of adversary samples will be different from that of normal samples. Thus, the concept matrix of adversary samples and normal samples serve as the diagnostic indicator for the model. So based on the mechanism we have introduced, the proposed DNN offers 3 tiered diagnostics. First, we perform concept pattern analysis. We identify and detect which concepts are common for both adversary samples and normal samples, we identify which concept the adversarial attacks use to manipulate the model's decision. Secondly, we implement special pattern analysis. Lastly, we have, as we mentioned, DNN-GP has a pre-trained decoder. Thus, we can reconstruct the adversarial samples and check how the reconstruction results are different from the original adversary samples to understand how the knowing structure perturbation works. So we first show the result of concept pattern analysis. We study how difficult kind of adversarial attacks are different from the normal samples in terms of the concept usage. Attacks include like FG, SMO, PGD, GSMA, deep-full, CW, and PIX attacks are also considered in this study. The takeaways are that different attacks have different strategies in manipulating the normal samples. We find attacks such as FG, SM, and PGD are more likely to change many concepts to enable attack success, while some attacks like deep-full and pixel attack focus on leveraging specific concept to launch attack. We also study how does adversary examples of data corruption samples change in the conceptual space compared to normal examples for demonstration. We study the color shift and rotation attacks, as we can see in the left subfigure. The color shift and rotation create adversary examples by manipulate the color in the face object and rotate the object. In the right subfigure, we map the original sample and the adversary samples into the conceptual space. We can see that in the latent representation space, the latent feature reflects well the manipulation in the pixel space. So that is the color shift attacks are successful because the facial features are changed. The rotation adversary examples are successful because the face feature is rotated. So lastly, we study whether the knowing structure perturbation in adversary sample example can be explained in a structured, meaningful explanation by DNN-GP. This is done by mapping the adversary samples into the latent concept matrix, and then uses the decoder to reconstruct the sample. For demonstration, we use FG-SM attack on NIST dataset as an example. As we can see, by comparing the original sample, the reconstructed vision of the adversary sample, for the first sample 9, the attacker chose to fill in the black spaces of the number 9 to forge it into a 1. In the second sample 2, the tail of the number 2 is weakened, leading to its reconstruction as a 0. The third sample 7 shifts the upper stroke of the number 7 to the right, connecting it at the tail, causing it to be classified as 2. The fourth sample 6 merges the bottom half of the number 3, forming a circular shape, making it resemble the number 6. The takeaways here is that reconstruction of adversary examples through DNN-GP can help to understand how knowing structural perturbations work in a structural manipulation manner. So we conclude that the proposed DNN-GP is a high-level abstract diagnose result for various model faults by mapping the high-dimensional input to a low-dimensional latent conceptual space. One limitation of DNN-GP is that it only considers the vanilla VQ-VAE structure as an investigation. So therefore, future research direction can try advanced VQ-VAE to improve the current DNN-GP structure. So other future directions also include study other domains like adversarial examples in text and audio. In addition, studying how to use DNN-GP to improve the robustness of the model is also worth investigating. So thank you for your attention in this work. So for any questions, please feel free to contact the others. Thank you.
Thank you, Zhao.